Hi everyone, we're starting chapter 8 today, and in chapter 8, since we just finished a nice good review on logs and exponentials, what we're going to do is we're going to move into the calculus part. And today we're going to start talking about limits of log and exponential functions, and then next we'll do the derivatives. So let's start with a quick limit review. It's been a little while since we've done them. When you're doing a limit, you always try direct substitution first. And that's going to be true for logs and exponentials too. So this is mostly if you're doing like the limit as x approaches a number. X approaches 2, x approaches -10, something like that. If that happens, plug the number in and see what happens. If you get a result of an actual answer, a constant, that's the answer to the question. So here's a quick example. Let's say I asked you to do the limit as x approaches 1 of e to the x minus natural log of x. Well, what you do is you'd say, all right, well, let's start by just direct substitution. Let's just plug in 1 for x. So that would be e to the first power minus natural log of 1. And e to the first power is e. And natural log of 1 is 0. Remember, any log of 1 is 0. So what you get is e minus 0, or just e. You could call it e, or you call it e to the first power. That's fine too. But basically, that's your answer. So if x is approaching a number, then doing an exponential or a log limit, or both, like this one, it's the exact same as we did before. Just plug in the number and see what happens. So what I really want to focus on for today is the limits as we approach either positive or negative infinity. And let's start with positive infinity. So first of all, when you're approaching positive or negative infinity, what you're talking about is end behavior of a graph. As x approaches positive infinity, that's saying what happens way, way, way off to the right, as x turns into a really big number. And as x approaches negative infinity, it's the left end behavior. Now, when you substitute, I put that in quotes because you don't really substitute infinity. But we talked about the first time through, we talked about when you're doing direct substitution with infinity, what you want to do is just say to yourself, if I put in this really, really, really big number for x, what happens? And that led us to a conversation about what we call the principle of dominance. So, many different functions go to infinity as x goes into infinity. Basically, think of it like this. If you're graphing a function, I'm going to squeeze it in right here, the function can do anything at all, but if it ends up with an arrow to the right, like this, that means that the function is going to positive infinity. Or if it turns downwards, it's going to negative infinity. Now, a lot of different functions do that. But we talked about how some of them get there faster. You can have two different functions going to infinity, but one of them is still a much, much bigger number. And that led us to what we call the principle of dominance. And that says if you have two different functions, and they are both going to positive infinity, then only the bigger one matters. So what I want to do right now is pause and go to Desmos and investigate some different functions and look at what happens, what that means, like what it means to go to infinity faster or to be bigger when you reach infinity. Okay, so here we are in Desmos. We're going to look at some familiar functions here. Let's start with a polynomial function, like a simple one, like just x squared. And then I want to do a radical function, so maybe I will do square root of x. I want to do an exponential function. Let's do e to the x. And I want to do a log function. So let's go with natural log x. And let's kind of slide it down here. So we're looking at what's happening as you approach positive infinity. Now what you see is four very different graphs. The green one and the red one, which is our exponential and our polynomial, those are definitely going to infinity. Those are shooting almost straight up in the air. They're getting there fast. The blue one, which is square root of x, and the purple one, which is log of x, or natural log of x, those are going to infinity, but very slowly. They are going up, 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 but they're kind of flattening out. Now, if I asked you guys the question, what is the limit as x approaches infinity for all four of these functions? It's the same answer. The answer is positive infinity. But you can see the green one is getting there fastest. That's the exponential. The red one is the next fastest. Then there's a big dip down to the blue one. And the log one is the slowest. And that's going to lead us into that, what we called the principle of dominance. All right, so here's basically what we just saw on Desmos. As x approaches positive infinity, an exponential function is bigger than a polynomial function, which is bigger than a radical function, which is bigger than a log function. The logs are the smallest of the four. Now, within each function type, you also have dominance, like some exponentials are bigger than others, and some logs are bigger than others. So for example, with exponentials, it's all about the base. The bigger the base, the bigger the function. 9 to the x is bigger than 5 to the x, is bigger than e to the x, which is bigger than 2 to the x. So for exponentials, the biggest base always wins out. Same for polynomials, the biggest exponent. X to the 6th, bigger than x to the 5th, bigger than x squared, bigger than x by itself. So again, those two are pretty straightforward. The bigger number is the more dominant function. Now with the radicals, you want to be a little bit more careful. So basically, the bigger the root, the smaller the function. You get an inverse relationship. And I'm not going to Desmos to do each one of these because I don't want this video to be an hour long, but I encourage you to, pause the video if you want, take a minute and go graph these on Desmos and look at them, compare them. But basically, like if I did a quick sketch for my radicals, my square root of x might look like this. And the cube root of x might be a little bit smaller. And I'm just doing positive infinity, I'm not drawing what happens to the left. And the fourth root might be a little bit flatter than that. So basically, the bigger the number on the radical, the flatter it gets. Now they're all still going to infinity, but again, some of them are getting there a little bit slower. And then you get a same relationship with the logs. Basically, the bigger the base, the smaller the function. In fact, it looks very similar to what we just drew with the radicals. The white one might be log base 2 of x. The yellow one might be natural log. The green one might be log base 3. If I did log base 100, it would be very flat. So you get the idea. We have this basic structure where exponential is the biggest, then polynomials, then radicals, then logs. But then you have like a subgroup within each one. So keeping that in mind, let's do this for an example. I gave you a bunch of functions, and I want you to put them in order, or we are going to together put them in order from biggest to smallest. And I put that in quotes. You know what I mean. As you're going to infinity to positive infinity, which one is the biggest and which one is getting there but not very quickly. So basically, if I'm doing this question, I'm going to start, like we said, with subgroups. I'm going to say, well, I know of all of these, the biggest ones are the exponentials. So let's start with those. If I just look for exponentials, I have an e to the x, I have a 2 to the x, and I have a 3 to the x. Now remember, e is about 2.7. So e to the x is going to be in between 2 to the x and 3 to the x. So of the three exponentials I gave you, the biggest one would be 3 to the x. The next biggest one would be e to the x. And the last biggest one, or the smallest of the three, would be 2 to the x. All right, I'm going to scratch those out. And then I'm going to say, well, the next category would be my polynomials. So let's look for polynomials. I have an x squared. I have an x cubed. Now that x to the 1/2, that's actually not a polynomial. I threw that in there to kind of remind you, almost trick you, remind you of some properties of exponents. X to the 1/2 is actually the square root of x. It's not a polynomial. So don't group that in with those. Instead, we only have the 2, and the rule is simple. Bigger exponent is bigger function. So after 2 to the x, I would have x cubed and then x squared, and we've used those two. Now after that comes radicals, and for our radicals, I have a cube root of x, and then we have that x to the 1/2, which I already rewrote as x squared. So of those two, if we're going biggest to smallest, the bigger one is the square root of x, and the smaller one is the cube root of x. Remember we said with the radicals, the bigger the number, the smaller the function. So I've used that one and that one. And now we have the 2 logs left for our last 2. One of them is natural log and one of them is common log. Natural log is base e, which is about 2.7. Common log is base 10. So the rule for logs was smaller base, bigger function. So for my last one here, I would do natural log first, natural log of x, and common log last. Natural log is bigger because the base is smaller. So I kind of color coded it to make it stand out. In purple, we have our exponential functions in order, 3, then about 2.7, e, then 2. In green, we have our polynomials. X cubed is bigger than x squared. I think those first 5 are kind of obvious. Bigger number is bigger. The last 4 are the ones you want to be careful on. Make sure you really understand the concept of like which radicals are bigger, which logs are bigger. But that's going to lead us into how we do limits. So we go back to the principle of dominance, and what it comes down to is when you're doing a limit as x approaches infinity, if you have more than one of these functions in the question, all you got to do is find the biggest one and say that's the one we're going to work on. So the principle of dominance says if x goes to infinity, x going to infinity means you're just going forever to the right. You can get as big as you want. And you're saying if 2 functions are even just a tiny bit different, like our square root graph and our log graph, those looked pretty similar when we graphed them next to each other. If I go far enough to the right, if I pick up a big enough number, they will have separated so that the square root one is so much bigger than the log one. The log one just becomes insignificant, and we count it as a 0, basically. So all of a sudden we have this question here, which looks tough, but is actually very easy. You guys will see. We have the limit as x approaches positive infinity of this very complicated looking function. 3 to the x minus natural log of x plus x to the 100 all over 2 to the x minus 7x squared. So I look at it and I say, well, because this limit is approaching infinity, remember this is only for x approaching infinity. Because the limit as x approaches positive infinity, all I have to do is pick the dominant function. So I can do this. I can go, it's definitely not the natural log, that's a small one. It's not the 7x squared. It's not the x to the 100. Now I threw that in there again almost to trick you. You look at that and you're like, x to the 100th power, that's really big. But it's not compared to 3 to the x because we're going to infinity. If I put in a big enough number for x, 3 to the x becomes so much bigger than x to the 100 power that x to the 100 just kind of disappears. So our polynomials are out, which leaves us with a 3 to the x and a 2 to the x. Those are both very big functions. They're both exponential, but again, the rule is the 3 to the x is bigger. And as I go to positive infinity, that's the only one that matters. That's the one. And that one's going to positive infinity. So basically what I get is essentially infinity over, I'm going to put 0, it's not really a 0. When I put a 0, what I mean is very small. Basically 0. And if I take my infinity and I divide by a small number, it gets even bigger. So infinity divided by something very close to 0, the answer is just infinity. So you got to find that dominant function. Everything else goes to 0, and then you basically just give the answer. So if you understand the principle of dominance, infinite limits become very simple. Let's talk about negative infinity real quick. Negative infinity is what's happening to the left instead of the right. And I want you to really focus on the graphs, just like we did. I'm not going to open up Desmos again, but if you want to, you can. If you ever need to, you can. But infinite limits, positive and negative, are end behavior, and they have a lot to do with the graphs. So here's some differences. This is why I said negative infinity is different. Number one, every exponential goes to 0 on the left. If you remember when we graphed exponential functions, they all look like this. They have an asymptote at 0, and they do this. Now what we were focusing on when we opened up Desmos just a minute ago is this part right here. We're saying, yeah, that's going to infinity, and it's getting there really quick, straight up. But see, now as you're going to negative infinity, it actually has an asymptote. It's flattening out at 0. So for any exponential at all, it could be e to the x, it could be 10 to the x, it could be 1 billion to the x. The limit as x approaches negative infinity is 0. So they are the least dominant function on the left. Towards positive infinity, exponentials are the most dominant function. On the negative side, they're the least dominant. Number two, radicals and logs don't even have a limit as x approaches negative infinity. Neither one is defined. You can't put a negative number for a radical, at least not for an, I should say, an even numbered radical. Even powered radicals don't have a limit to the left, like the square root of x doesn't. The cube root of x does. And then no logs do. Logs you can't put in a negative. So I should say some radicals and all logs don't even have a limit on the left. So for our last example today, let's repeat the example from before, but go to negative infinity instead of positive infinity. And the way the question is written, without doing any work at all right now, basically because of this one right here, the answer to this question would be does not exist. Principle of dominance does not matter if you can't do one of the functions. So, what I'm really saying here when I say x approaches negative infinity, I'm saying x is a really big negative number. Well, if I put any negative number into that natural log function, it's undefined. So automatically, because of that one function, the answer is does not exist. But I do want to do a problem, so let's do this. Let's kind of take that one out. Let's say, and it's not actually equals, let's say this is a new question. Let's say we're doing the limit of, and I'll copy the question exactly the same way, 3 to the x, not 3x, to the x plus x to the 100 over 2 to the x minus 7x squared. Okay, so I just kind of recopied the question. I threw that natural log out. I said, let's make one that does work so we can just see how this works out. And also, you know what? I copied a couple things wrong. That's not infinity, that's negative infinity. Limit as x approaches negative infinity. Okay, so we're still doing principle of dominance, but this time we're doing end behavior on the left instead of the right. So right off the bat, like you don't want to do the same thing we just did where you think, okay, well I see that 3 to the x, that's my dominant function, so I'm going to focus on that one. Because both of those functions are actually going to 0. Like you are literally getting an answer from the limit as x approaches negative infinity of 3 to the x and 2 to the x is 0. So this question is really kind of like saying the limit as x approaches negative infinity of just x to the 100 over negative 7x squared. And now you can use the principle of dominance. You can say, all right, now which one of those is bigger? So if I take a look at those two graphs, if I graph, we'll do x squared first, and don't even worry about the negative 7 for right now. If I were to graph x squared, it's a parabola, and it looks like this. So it's up on both sides. It's going to positive infinity on both ends. Now, if I graph x to the 100 power, what you actually get is a much, much skinnier parabola. Now, skinnier means bigger, because if I kept this going and going and going and going, it's going to be way, way, way higher than the white parabola at equal x values. So what we're saying is, this time I'm doing negative infinity, so I'm doing the left end behavior over here. I'm comparing this arrow here to this arrow here. Now, both of those are going to positive infinity, but the blue one is the dominant function. So basically the blue one is what matters. Now, the one thing you do want to do to answer this question is you want to realize, okay, yeah, this is my infinity function right here. This is basically going to 0, but not officially going to 0. It's very close to 0. And that's important because it is negative, and you have to count that. So you want to realize my final answer is going to infinity for sure, because the x to the 100 was on top, and that's going to infinity. But that x to the 100 is positive, and the 7x squared is negative, and positive divided by negative is negative. So the answer here would actually be negative infinity. And that's one of the tricky parts about these. When you're using the principle of dominance, you're deciding which function matters, but you still have to take positive and negative signs into account, because you got to decide whether this thing is going to positive infinity or negative infinity.